Hey, hi guys. Good morning.
Hi, good morning, Shiva.
So just give me 2 more minutes so that. Okay, so let's get started. So on our last session on HDFS, so we were just discussing the characteristics of it. So just on high level. Okay, so I didn't go into much deeper. So just to give you a quick recap. So what happened? What we discussed on HDFS. So HDFS is mainly designed for large amount of data size files, so huge size files, and its one more notion is write once and read multiple times. Okay, and so second property is fault tolerance. So mainly ability to store large size files. Second is fault tolerance on them, and data locality optimization. So this is during the processing. Okay. So how it achieves this ability to store large files with the help of blocks concept. So this is its characteristic. It achieves this by this concept. And fault tolerance is achieved by replication factor concept. Okay. So data locality optimization is achieved by distributed processing. Okay. So now let's get into these topics. So how exactly it divides the data into the blocks and all. The limitations also I have listed down in our last session, but I didn't justify the second point. So write once, read multiple times. That means once written, that's done. So you can't update we cannot update or delete a record or insert a record into HDFS file. But what all you can do, you can write once, and after that you can appending records to it and deleting entire file, reading record by record. So these are the operations that are supported on your files, HDFS files. Okay. So let me put these things aside for some time. And it is one more limitation is that not a good idea to store small size files. Okay. So why this is not a good idea, I will explain you once you understand the responsibilities of name node and data nodes and the blocks concept. Okay. So let me put these limitations aside for some time. Let me jump into the design concepts. Okay. So mainly in the HDFS architecture, we have seen one edge node which acts like a client and one master node. So this is a master-slave architecture. I was explaining you, right? So HDFS is nothing but a master-slave architecture. So one master, multiple slaves might be. Slave 2, slave 3. So this master, we call this as a name node. And these slaves, this is DN1, data node 1. This is DN2. This is DN3. And to interact with these, let's assume we have only 3 data nodes in this. But in real time, there can be up to some 20s, hundreds, even thousands also sometimes. Okay. So there is an edge node. We also call that as a client node. Okay. So from that client node, we interact with HDFS. Okay. Now coming to the components, we see those different types of nodes there. One is edge node, which is useful for interacting with, or which acts like a bridge between the actual end user and the HDFS cluster. And inside the HDFS cluster, main important components, so the name node and data nodes. And the third important concept in the architecture is the blocks, right? So this is as per the HDFS 1 architecture. You guys know that Hadoop 1 and Hadoop 2 releases are there. So Hadoop 1 is the older one until Hadoop 1.x all releases. Okay, even until Hadoop 1.9 version and all. So from Hadoop 2 and 2.x versions onwards, so our MapReduce got replaced, MapReduce framework got replaced with Yarn framework, which is also called as a MRv2, MapReduce version 2. So let me show you the architectural differences also between these two. So earlier we had name node and data node in terms of HDFS. So when was Hadoop 2. Released? Almost like two 2 years and 2.5 years back. So already, yeah, I can say almost like 2.5 years back. Okay. Around the beginning, early 2013, 14, 15, 16, or in the mid of 2013. Okay. So in terms of HDFS, the architecture is same between your HDFS 1 and HDFS 2. There are minor differences, so that we'll discuss later. So the masters are name node in HDFS, job tracker in MapReduce, and the slaves are data node in HDFS and task tracker in MapReduce. But in YARN architecture, this job tracker and task tracker got replaced with, so job tracker got replaced with resource manager and task tracker with node manager. And the supporting machine, the supporting resource or supporting node for the name node is secondary name node. How will it support? By sharing some of its responsibilities. What they are, we will see in the coming slides. Okay. So before even that responsibilities, so first you all had a questions like, when you upload a 1 GB file, how will it get distributed across the machines that you have? Okay, suppose, as I was telling, HDFS is nothing but Hadoop distributed file system. So whatever the file that you upload or write into your HDFS, that file should get distributed. So distributed across the data nodes. Need not be into all the data nodes. So based on the parts that we divide that file into. Okay. So generally HDFS divides any file into some equal chunks or equal parts. So whenever I use any of these terms, they refer the same. Okay. So one big file is divided into these many parts. And when that is dividing, it chooses the block size according to your configuration parameters that you have set up in your cluster. In Hadoop 1, it was 64 MB, and still you may see this in so many places, in blogs and some websites and some old textbooks. But as per the Hadoop 2.0 architecture, the block size is 128 MB. So the default block size is 128 MB. And in some of the Hadoop 2.5 onwards or the above releases, you might observe your admins might change that to 256 MB also. Okay. So we have used in some of our clusters even the 256 MB block size. So this dividing a file into blocks is not something newly introduced in just the Hadoop. Even in traditional file systems like your NTFS or ext2, ext3, NTFS is for Windows-based file system, right? And ext2, ext3, ext4 are Linux-based file systems. So even there, the files will have blocks, but they were around 512 bytes or max of 1 KB or 4 KB max. 4 KB blocks in a regular file systems like ext4 or something. This is a Linux background, the file system format type. So in this, so whenever you upload a file, let's say I have if my block size is 4 KB, if I have 4 MB input file, okay. So if I load that file into ext4, so then total of this is 4000 KB, right? So almost like 1000 blocks. Here you should understand why the block size is so high in HDFS and why it was low in, and I mean, we don't need to worry why it was low. So especially you should understand why the HDFS developers made it as very high. The reason is, if you know the reading process of any disk or any file during your IO calls, so ideally, so when your data is present in your disk, they will be having some circular read disks, right? So during the read time, so if this is your, let's say this is your hard disk, okay? Your hard disk, inside of your hard disk, you will have your data stored in that circular rings fashion, okay? So this we call as a redundant RAID disks kind of stuff. In order to read any file, let's say that file is written from, so this much to this much of size, and this is of 4 MB file. And if you have that file divided into blocks each with 4 KB, so now you have almost like so 4 KB into each block. And in order to read that file, so it reads block by block into RAM memory. Okay. So with one IO call, with one input output call, with one read call, it gets one block into RAM memory and it processes that 4 KB, and again it sends that seek to the next block to read the next 4 KB. After reading that 4 KB, again it sends the seek to the disk seek to the next block. That means here almost you are making 1,000 read calls. So 1,000 times making 1,000 times the read calls or IO calls. We call these as input output calls to your disk to read complete reading of that. So for every 4 KB, you have to move your cursor from one block to another block. So that moving that cursor from one block to another block, we call that, in terms of IO terminology, we call it as a seeking. So we call that as seeking. So you have to make 1,000 seeks. So this seeking time will result in the slow performance if you have these many seeks. On the other hand, let's assume so that entire 4 MB itself is present inside a one block with one IO call. So here in this scenario, let's assume you have 100 MB file. Okay, so 100 MB means 64 MB is one block and remaining, so 64 MB plus 36 MB. Okay, so in the first seek, in the first request, it will read the 64 MB, and the second request, it will complete reading the 34 MB. So you're just making two input output calls to read the entire 100 MB also. Whereas you are making just 1000 input output calls just to read 4 MB. So to read 100 MB, so 1000 into 25. Okay. So even in the traditional file system, they come up with some kind of optimizations and reducing IO seek times and all those things. So they did it. They did a lot even in traditional file systems to overcome this or improve the read times. But still, so there is a lot of performance gap, or there is a lot of IO calls to read that. So that is the notion, that is the idea behind why Hadoop founders. So what is the minimum file size in HDFS? So minimum file size in HDFS, so recommended file sizes to go with in HDFS, so minimum of 128 MB files. Okay, but ideally speaking, this is not possible always in real time. Okay, so that's why it supports you to store any file size, even 1 KB file you can store. But as per the Hadoop's design, it recommends you to combine such a small files. If you have huge amount of such small files, it asks you to combine them and process them together and remove all these small files. Okay, so ideal file size, or as per the best practices, we recommend to store file sizes of at least 100 MB or even more than that. So in case if you don't have option to store small files, that is okay, but they should be minimum in number. They should not be like millions. They can be up to hundreds of small files, max up to thousands, but not into millions. So millions of small files storing in your HDFS causes a problem on your name node. So how does it cause? So even that I'm going to cover now. So here, so my 100 MB file got split into two blocks. If I take 64 MB as the block size, as per the Hadoop one, or if I want to take as per the Hadoop 2 architecture, so where 128 MB is my block size, if I consider 200 MB input file, so 128 MB is the first block, and remaining, so 72 MB is the second block. So this is the default block size. This is how it gets split. Now, your question, you may raise question, even the second block will really occupy just the 72 MB, or it will occupy 128 MB and remaining space might be empty. So people might ask this question also. Whether you allocate 128 and 128 to 56 MB, out of which 56 MB is empty, or you will just occupy the 200 MB. So will it be better to split 200 into 100 MB plus 100 MB? Okay, But what if you get 210 MB? Then will you make it 105 MB, 105 MB? What if you get 220 MB? I mean, is your question like, so why are we, I mean, can we split into exactly half of this, that file?
Yeah, actually, exactly. I want to ask, is it always a good practice to share the load between the machines equally versus the last machine should get the leftover load? Which one is a better practice?
Load balancing between the machines as a developers or as end users, we don't need to deal with that. Even admins, they don't, they don't deal with that. There will be one configuration property. So just that once we have set up, and even if we don't alter that configuration property, by default, it comes with your data nodes will equally get balanced. Okay. It's not like if you have 10 data nodes, only 5 are overutilized and 5 are underutilized. That scenario will not happen. So your name node is responsible for that. So your name node will keep on observing, and it will make sure that it will make sure that all the data nodes are almost equally balanced. Okay. So there is a percentage allocation that any data node should not go beyond the plus or minus. So plus or minus. So 10% deviation from the average workload of a average workload of a machine. Plus or minus 10% deviation. So that means on an average, one data node is storing 1 terabyte. So then if this is the average storage of one data node, then any data node, if you take out of those 10 data nodes, it should not be more than 1.1 terabyte, or it should not store less than 0.9 terabytes of information. So it can be between 0.9 terabytes to 1.1 terabytes range. It is not possible to make exactly 1 TB equal in all the data nodes, right? So that's why they use plus or minus 10% deviation from the average workload or storage load of the data node.
Okay.
Okay. And splitting your data always into 2 equal halves will not make sense. The reason is, if you have 1 GB file and splitting that into 500 MB plus another 500 MB, you are again going against the the notion of the one equal block size across the cluster. Okay, so here you have some blocks with 500 MB and some blocks with 100 MB, and so that way, right? So ideally, the block sizes across the cluster maintain the same size. It could be max of 128 MB block or less than that. Okay, so if you store 200 MB file onto your HDFS, it will get split into 2 blocks. So those 2 blocks, the first block will be always of the max size that it can fit into, is 128 MB. So this block occupies 128 MB from your disk. And the second block, so ideally the block size is max of 128 MB, right? But when you don't have that much of data and you have just 72 MB, your second block will occupy just the 72 MB. That means your 200 MB file on HDFS reserves only 200 MB storage capacity. It will not occupy 256 MB. Okay. So people will get, I mean, this doubt most of the times. So that is one thing. Next, coming to this, your edge node or client node is uploading this 200 MB file. So where will it send the request to first? It will send the request to name node, and name node will identify which are the data nodes that can store this file and which have capacity to store the blocks, right? So storing the file means storing the blocks. So let me explain. I have one diagram to explain that right anatomy, then you can better understand. Okay, so in order to explain that slide completely, I need one more topic support. So as part of ability to store large files, it splits those things into blocks. And to maintain the fault tolerance, so every block is copied into 3 copies. Okay, so every block is maintained in 3 copies, so that if something happened, something weird happened, even if 1 block is lost or 2 blocks are lost, the 3rd copy will be available on your cluster, and you can easily read your data back for that file. Okay. I think this picture clarity is not there. Either this one or I think, is it visible? Not sure. Okay. So in the Hadoop distributed file system HDFS, there will be one name node and multiple data nodes, right? So, and one client. So it is saying that people sit in front of me and ask me to read or write data from edge node. And name node is saying that there is only one of me, and I coordinate everything around here in HDFS. Okay. And data nodes are saying that we store the data and there are many of us. Okay. The text is something bit blurred here. So even if you are not able to understand, that's why I'm reading out. I know this text, right? Okay. So there are many of us, sometimes even thousands. So this is about this HDFS. Okay. So writing data into HDFS. So I got a request from user, and this user, let's start with writing some data. So this user is asking this client machine or edge node. So Mr. Client, please write 200 MB data for me. And then client accepts that request. It will be my pleasure. So are you not forgetting something? It's asking, a client is asking the user, so are you forgetting something? This user is telling that, oh, yes, please divide the data into 128 MB blocks, copy each block in 3 places. So here, especially this box is done one time by the administrators. Not like every time you upload a file, the user will tell, I want this to be divided into 128 MB or 256 MB, or I want this to be done. How many replicas on those things? Okay, ideally. So assume your client node or edge node got the enough information that it got the basic configurations files that are present. So it knows now it knows the block size, which is of either 64 MB or 128 MB, and it knows the replication factor. So how many replicas of your block should be? Okay, so by default, usually it is 3. Replication factor, each block is stored in multiple locations, usually 3.
Shiva, what determines whether it is 128 or 256?
There is a one property, dfs.blockSize. In the HDFS site.xml file, that property, looking into that property, it identifies into how many what size of blocks it should divide into. Okay, is that your question or something else?
Yeah, I mean, why, what is the judgment to store between 128 versus 256? When would I use 256 and when would I use 128?
Okay, so I explained you the reason why we need to go for, okay, let me stop this. This 2.5 was a little slow yesterday. I'll suspend this. Let me start this, my VM as well, and then I will explain you the reasons. Let it get loaded. Yeah, so I explained you the reason behind why we are going for bigger block sizes, right? So if I have 128 MB block size, and if I need to read 200 MB, so I will be making just 2 IO calls and reading 128 MB block one at a time into your RAM memory. So you have reduced from thousands of IO calls to just 2 IO calls. And as you know, HDFS is designed for huge size files. Let's say I have received some trending data for a particular store or something for over a period of 1 year. And if I want to read that entire data, so that data might be around 1 TB. Okay, so if you take 1 TB of one table itself, and if you want to read that entire, again you are making thousands of, even if you divide that into 128 MB blocks, there will be at least thousands of blocks, right? So that means thousands of IO calls, and reading 128 MB blocks into your RAM. So suppose if you have very high-end server configuration and your RAMs are enough, you have enough storage to store even more data into RAM, then you can double this size that you can store into RAM. Let's assume this is the configuration that when you had a 256 GB RAMs, 256 GB RAMs on your data nodes. Okay, so but you bought or you upgraded your hardware to either 512 GB or 756 GB or 768 GB. 768 GB RAMs. So that means you have plenty of RAM memory available. You can read even the huge blocks at a time into your RAM memory. And when you have really very huge files, terabyte size files, so one table file size itself is a 1 terabyte around. So when you use 128 MB, let's assume there are 2000 IO calls. 2000 IO calls are there. I mean, I'm not dividing and I'm not finding exact number. So if you use the same 256 MB here, so that will get reduced to half of the IO calls, right? And here you made the speed, you made double the speed. But the problem with this 256 MB is you should have enough RAM memory available. You should have sufficient amount of RAM memory available on your data nodes. Because that much of, let's say, there is a concept, I mean, you'll get complete understanding once you understand the yarn, once I complete the yarn architecture as well. In yarn, we'll split this 256 GB RAM into some containers. And in each container, they will have the, for node manager, for each node manager, how much RAM memory it gets. Okay. And inside that node manager's allocated RAM memory, main memory only. So these blocks will get stored during the, so inside those containers, the node manager JVMs will have the specified RAM memory. Inside that RAM memory, it should store that. So if that node manager RAM memory itself is low, that means it is just 1 GB. You can't read more than 8 blocks of 128 MB or 4 blocks of 256 MB.
Yeah, that makes sense. Thank you. Is there a industry standard algorithm or something? Is there
industry standard algorithm in the sense, most of the times, if you are not exceeding, at least if 20% of the data, 20% of the data sets that you have on your enterprise organization are more than some 100 GB file size, then you can go with bigger configurations and go with 256 MB block sizes. At least 20% of your data sets. Okay, so if you don't have, and your max file sizes are like 10 MB, 10 GB or 20 GB files. So at max, you have 20 GB file size or 30 GB file, 50 GB files. So then you can stick to 128 MB block size. And 64 MB is no longer valid. So nobody is using, but my knowledge, nobody is using 64 MB these days into the clusters. So 128 MB is the fixed one. Okay. So yeah, that answers your question.
Shiva, sorry, one more thing. What do you mean by 20% of data set? What exactly was that?
20%. Okay, 20% of the data sets means you have 100 data sets on your from your enterprise organization. So there can be smaller data sets, like 80 data sets can be of 1 GB, 2 GB, 10 GB, 20 GB. But at least 20 data sets should be size more than 100 GB.
Got it. Perfect. Thank you.
Okay. Okay. So here, so the properties, as part of yesterday's session, I was telling you any configuration related stuff in your Linux machines will be present in etc folders, right? In etc/etc Hadoop, if you go into Hadoop, so conf, inside that conf folders, So the core properties common to both HDFS and yarn and MapReduce, anything that is common to HDFS and yarn and MapReduce, they will be present in core site. Okay. So anything that are specific to HDFS, you will find them in HDFS site.xml file. So here you can see DFS dot block size being externally set up, or if it is not explicitly set up in this site.xml file, this will be present in your default.xml file. DFS means distributed file system dot. So this is not there. And the replication, yes, it's there in the first property itself. So I have DFS.replication set as only one, because in my quick start VM, this is a pseudo cluster, right? This is not a real-time cluster. This is a pseudo cluster. And in my cluster, I have only one data node running. If you see, there is only one data node process is running with process ID 2020. So with one data node, I can max setup, I can store only one copy of the blocks. So achieving your replication fault tolerance in your quick start VM is not possible. But I will show you these basic properties and where it gets stored and the blocks where it gets stored in the real-time cluster. I will show you that as well slowly. Okay. So if any of your configuration properties, if you don't find them in your HDFS site.xml file in your etc Hadoop conf folders, they will be present in your HDFS-default.xml file. That are, if they are related to HDFS. If they are related to MapReduce, you'll find the mapred-default.xml file. And for yarn, you will find them in yarn-default.xml. Okay, so mainly you will have 4 site.xml files, and corresponding to these 4 site.xml files, you will have 4 default.xml files as well. And those default.xml files will not be part of your conf folders. By default, it gets them by the documentation itself. It will maintain under some share folders inside your user lib. So, I mean, ideally speaking, developers rarely bother about these properties. They don't bother about these configuration files. So that will be handled by your administrators. Don't need to worry. So this documentation, the share folders also not present. If you don't find the default.xml files in your conf folders, you can just get them from the Google. It's the same. Okay. According to your HDFS version that you are running, so let's say if you want to know HDFS default.xml file for HDFS 2.6 or something. So this is 2.4.1 release, HDFS default. This is for, you should refer the Apache Hadoop versions only. Let me take this as an example. You will find these files for every release. Okay. So you might not be interested in understanding all these properties, but anyone whoever is interested in mastering the admin skills as well, and how do you control the your HDFS working properties, you can just go through these things. Okay. Here, so if you can see, some of the properties that I can tell you are like, so this gives you the dfs.namenode.name.directory. So in name node, where exactly then all the name node files will be get stored. Okay, and shade edits, those things will tell you slowly. And in data nodes, actually the data, where exactly the data will get stored in the local file system. So this gives you the path. Okay, this is again another variable. So temp directory that it stores there. And here you can see the properties that I was talking. dfs.block size. This is in terms of bytes. And if you convert these bytes into MBs, it will come into 128 MB, such as this means 128 MB. You can see. So the default block size for new files in bytes, you can use the following. This many number of bytes means that in terms of block, in terms of MB, that is 128 MB.
So, Shiva, we cannot change, we cannot have multiple blocks, like 128 for some and 256 for some?
No. You can, while writing a file, you can specify, see here, controlling this block size at file size, ideally not recommended. This is a cluster-wide property. Once you set up in your HDFS site.xml file, across the cluster for all the files, it will be 128 MB. In case you want to force it for one file with 256 MB block size, yes, you can do that. Okay, so that property I will try to show you maybe during our MapReduce writing a files or something. So whenever I get some time, I will try to show you. But maintaining uneven block sizes in the cluster is not a good idea. Okay.
Not like similar to the traditional database where you have 4 MB, 8 MB, or 16 block sizes, right? That's whole difference.
Yeah.
Tables, right?
Yeah. So next, so the DFS dot replication property. So where it tells you the default block replication, how many copies of blocks will get replicated. Okay. So these are the default values that you can see here. And some of them, you may observe some other properties also. Like you can explore how much you want to checkpoint directory, data node directory, name node directories. What are the default directory paths for them? Okay. And yeah, and remaining properties may not make sense even if I explain at this point of time. Yeah. So just I'm showing you this file for your reference. If you want to find out any configuration related to HDFS and want to find the default value, you can refer to this file. Okay. So you don't need to find this file in your Hadoop installation itself. And those are default values. And if you want to override those default values, yes, you can override them by providing those same property names and changing their values in HDFS site.xml files. Okay. So why all of a sudden I entered into these configurations is because, yes, you can configure your block size of your own wish, and you can configure your replication factor of your wish. And that's where you do that. Okay, next. What happened to this? So next, in this diagrams, I have seen, so user asks the client, and client knows the block size and replication factor. So now, so divide the file into blocks. So the file is divided into, so this is of 128 MB, this is of like 72 MB. Okay, so first I divide the big file into blocks, and so this edge node divides that into the blocks, and it sends the block by block to, or it sends the request to name node. So Mr. Name node, please help me write a 128 MB block with replication of 3. Okay, so then name node will ask like replication 3. Okay, you need to find 3 data nodes for this client. So since it is asking for 3 replication, so at max 1 data node can store 1 copy. So that means if you have to maintain 3 copies, you should have 3 data nodes. Then how do I do that? Means it will have some metadata. Your name node will have metadata about all the data nodes. How many files that are stored, how many blocks that are stored on each of these data nodes. So that metadata will be present inside your name node. And whenever a new request comes from a client to name node, it checks that in the metadata file and identifies, so how many data nodes are less utilized, and on that those less utilized data nodes, how many blocks they can store. It gets that information and it identifies the appropriate data nodes, and it gives those data nodes back to the client. So here you go, buddy. Addresses of the 3 data nodes. I have also sorted them in increasing distance from you. Okay, so that means the closer data node will be the first one, and the next closer one will be the next data node, and the farthest data node will be the last data node that will be given to it. Okay, so your name node always try to give the closest data nodes to your client, and client took that, and client starts writing data to it. So I send my data, and the first data node only. So this client sends data to data node 1 only. Okay, so it writes to this data node 1, and this will, I share the data in hard drive. I mean, I will save the data in hard drive, and I will share it with my peer data node. Okay. So that way, client writes only into one data node, and that data node copies the data into another data node, and this data node copies that into another node. So that is what it is. While I am receiving data, I forward the same data to the next data node. And this next data node is telling that I will do the same what previous guy did. And this says that I am the last one in chain, so I don't need to copy anywhere. So client written 1 block, the first 128 block. So that got replicated into 3 places. So once all data for this block is written to hard disk, then send done to name node. It sends the writing of that block is completed. So that information will be sent to name node. And name node, so block successfully stored and replicated in HDFS. Then your client will be ready with, so when I'm done with a block, I repeat the same steps with the remaining blocks. The remaining second block, which is of 72 MB, for writing that second block, it repeats the same process. So once all blocks are written, please close the file. So case closed. Now I store all meta information in persistent storage. So or in RAM memory of this name node. Okay. So just a quick recap. What happened? I divided the file into blocks, and for each block, I provided addresses of the data nodes, and these data nodes are saying that we store data into the replication pipeline. Okay. So I think I'm getting questions. So name node also pass other data node info to first data node along with data. Along with data. Yes. Name node will not pass the data to data nodes. A client will directly write the data into the data nodes. So they will get the replication pipeline. So that means it sends the sorted order of your data nodes. Replication happens parallel or sequential. Replication happens sequential, right? So first it should receive here. So once after receiving, let's take that block is received here. Next, the block gets copied onto this. Next, that block gets copied onto this. And block is the smallest unit of storage that can be copied from one machine to another machine. Okay. And the same I have here. So let me try to make you understand. So HDFS client tries to create a file or write into a file. So there will be, this is like in terms of JVM, the distributed file system API will be there. It will send request to name node to create the file. And it will send the list of data nodes. And it will open FS data output stream object. So if you know the Java file read and file write operations, there we create data input stream, output stream objects, right? So input stream is for reading, output stream is for writing. So here in HDFS, we have that the subclass of those input stream and output stream classes. We have FS data output stream class, which is responsible or which can be used to write into a data node. So this is in terms of technical terms. So this is the object or output stream that writes into your data node. It writes that packet or the block, and that will get sent to the next data node, and that will be sent to the next data node. And this will send acknowledgement, this will send acknowledgement, this will send acknowledgement packet. Okay. And they will, it closes the FS data output stream object, so file writing object. And so once the file is closed, they will notify the name node that so and so file is written. So these are my block IDs. So this can store some block IDs B1, B2, B3, and the same B1, B2, B3 might got replicated into this. Okay, so they all tell us that So Mr. Name node, I have B1, B2, and B3, and even this tells that I have B1, B2, B3, and even this tells that I have B1 and B2, B3. Any questions? How it writes? On how it writes?
One quick question, Shiva. So the data nodes have to go through the primary data node to communicate with the client, with the name node, right?
Yes. To name node, they can directly. With the client, only the closest one gets communicated.
Oh, so in this diagram, this is for the client only. This is not for the name node.
Name node part I didn't highlight here. Okay, so name node, the communication between name node and data node, it will be there always. So for every 10 seconds, they keep on sending the heartbeat messages. We call them as the communication between name node and data node will be always there. That is through heartbeat messages. They send some information packages that I'm alive, I can still serve your requests. And along with that, piggy banking, we call piggy banking, right? So along with that information, if it receives any new blocks into it, it sends those block IDs to name node. And if it receives any new blocks, it sends that block information. If it receives any new block, it sends that block information along with that heartbeat messages. To keep update name node about its status, about its aliveness, and also it's the latest status about the blocks. Okay, so this one I don't need to specifically highlight, so that's why I didn't highlight this here. But so sending the acknowledgement to HDFS client is needed. So once this connection is established between your client and data nodes, so your client and data nodes are in good shape to communicate with each other, because instead of routing everything through name node and name node informing the client, that way there will be a lot of burden on name node, because this is only one in number. So this way your HDFS client can interact with, communicate with this data node, and another HDFS client can request name node, and it can allocate this data node and this data node and some other data node that is present here, and this data node can communicate with that client.
Shiva, one question. In this diagram, so the big HDFS file is sitting in the client machine only, because name node is just dictating the distribution terms, I guess.
Yes. So that big file, the big file is present in HDFS client. The 1 GB file or 10 GB file is present in HDFS client machine. From there to we are uploading here.
So name node just pass the instruction, it never gets the file.
It never gets the?
It never gets the file into the system. It just
no, name node will not get the file from client. So it at max the client sends the file size and the file name it wants to store with. Okay. So while you are uploading a file, it tries the same. It keeps the same file name on your HDFS. So it sends the file name to name node, and then this registry it registers that. So this is the file name, and it gets the file size also from the client. Then name node identifies that it needs these many blocks.
So name node machine doesn't have to have a very good high configuration, because all it's doing is just getting the information, and
it is just managing it, and it's just routing the work.
Mm-hmm.
You are correct, but one thing you have to keep in mind is that this is only one in number, where you have thousands of requests from clients, then your name node should have
Okay.
configuration to serve all of them in parallel.
Yeah.
Shiva,
Yeah, yes.
I had a doubt like, suppose there is a 1 GB file is there, it will
Mm-hmm.
be divided into some 25, 25 blocks, and it
Mm-hmm.
will be replica 3 or 4 times. Where who will do the replica name node or HDFS client?
Who will do that replication?
Yeah, because suppose there are now we have a 3 data nodes D1, D2, D3.
Mm-hmm.
There are 3 blocks.
Yep.
B1, B2, B3.
Mm-hmm.
Suppose B1 is replicated into 3 blocks, 3 data nodes into 3 times.
Yes.
Right?
Yes.
Who will do that one? Client or name node?
Neither name node nor client.
Okay.
Okay. So here I am showing you, right? So once
Yeah.
the block is copied onto your data node and your client tells the replication factor for that file in its configuration file, and even name node knows that the configuration file, the replication factor in the cluster, right? So then it sends, so for each block, so what are the 3 data nodes? To which 3 data nodes it has to write. So
Okay.
into the closest data node, in that pipeline, the client writes into the closest data node. And copying that into 3 copies will be taken care within these data nodes itself. So this data node will send it to the next nearest data node, and this data node sends to the third in the pipeline.
Okay. So that means there is a communication between the data nodes. It will they will pass the information to the other data nodes.
Yep.
Okay. Thanks.
Shiva, I have a question for you.
Yeah.
When the write happens first, if the client is writing the file to data node, for the data node, in that time, if write fails, what happens? The entire write fails, or will the framework take care of it?
That firmware will take care of. If this node goes down, it will try to give a one more try onto the next data node.
No, I'm asking for the first time when it is writing for the data node. I'm not like if for the first time when we write the data, then only the second it will be replicated to other thing, and it will be replicated to the third block. If the replicated block goes fail, then the framework will take care. What happens if the first block it is writing?
Yes.
Because replication happens sequential, not parallel. Where write happens parallel.
Correct.
Then if the first data node, if it happens, there is a chance that entire write may fail.
Correct. So that means you are telling that the step 5 write packet itself it is failed, right?
Yeah.
So it will not get this packet acknowledgement back to that.
Yeah.
So it waits for some configurable amount of time. So if it didn't receive the acknowledgement packet, then it tries to write the same block again into the same data node.
Okay, like if there is a failure in a data node, and until the heartbeat is given to the name node, it doesn't know. Until the write happens, it doesn't know that whether the data node has been corrupted or it is working.
Correct. You're correct.
So what will the scenario be in that case?
Okay. So this is one of the failure scenario where anyway, we have 3 types of failure scenarios that I will be covering in next. But anyway, since you asked, so if this node goes down, okay, and the client didn't receive the acknowledgement packet, so then it will again try to write into the same data node second time. Okay, so then also it will fail again.
Okay.
So it waits for 10 seconds or sometime, and if it didn't get the acknowledgement, again it writes into the same data node third time, and again fourth time. So it will make up to 4 attempts. So if 4 attempts failed, then it will mark it as this this write operation is failed, then it will report to the name node, and it will write into the next sequence data node. So again, it will write the same block into the next data node.
Okay, 4 chances are given for one data node.
Yep.
The write to happen.
Yep. Any task, it could be write task or process during processing also. So if one data node reading a block is failed, it will not marked as immediately as failed. It
Okay.
up to 4 chances. Even after 4 chances, if it fails, then it marks it as a something wrong with reading this file, reading this block, or writing into this block. Then if it gets this kind of hits very frequently, then your name node can mark it as a one of the red, or danger, or
blacklist.
It will put name node will put this data node into blacklist. There is a concept of blacklisting of data nodes as well.
Shiva?
Yes, Murli.
Something like in Apache proxy servers, if suppose in cluster environment, there is a proxy server is there, like a failover strategy. If suppose something like, if suppose the server is hitting a one cluster node, like data node, if it is not available for 4 times, it can go to the next node. Like that, it is any strategy is there?
Yes, like that only. That is how I am telling here.
So that means data one node, it will be hit the 4 times. If it is not there, it will intimate to the name node. Second time, after that, it will go to the
pipeline. So when HDFS client requested name node to write a block, it gives 3 data nodes. If this fails, and it picks the next closest one. Let's say this is the closest one in terms of network distance. This is the next closest one in terms of next network distance. This is the farthest one, among the given 3. Okay. So it chooses in that sequence. And this will write only 2 copies, and your name node will have a alert message saying that there are some blocks which are under replicated. So actually, a client asked for replication factor 3, and 1 is failed, and it copied only to 2. This means that block is under replicated. And during the next restart of your HDFS cluster, or when an admin runs the balancer command, then this 2 copies, this under replicated block will get copied onto the 3rd data node, making it again balanced.
Okay. Thanks.
Okay. It might be a slight confusing. This distributed processing itself means might be a bit confusing. But if you, thanks, Akila. If you just revisit couple times, so then try to understand. So I can even repeat the same topics again and again, not a problem for me. First, you should understand the basic building blocks here. Okay. And one more thing that I want to bring to your notice that, so I'm getting some suggestions from our members saying that taking it to 2-hour sessions, people are, the concepts are flooded over. Okay. So, if you feel like I want to reduce, if you feel like I should reduce the time duration for these sessions, I can even reduce. You can come up with your suggestions. Are you fine with 2-hour sessions, or you want me to make to 1.5-hour sessions, or even lesser? But obviously, it will increase the number of days. The course days will get increased. On the other hand, or you should be ready for either weekend, Saturday, Sunday sessions. Sometime may not be the same morning time, so evening time. Okay, so fine, no problem. You can go ahead with 2 hours. 2 hours is fine. 2 hours is good. 2 hours is fine. Okay. So 2 hours, every alternate will be good. Okay. Okay. Yeah. So means Monday, Wednesday, Friday, like that. Take the highest vote. Yeah, I will be taking the highest vote only. Yeah, but I received some suggestions from people, so I thought I will take response from everyone. That gives time to revise. Yes. Yeah, I agree on that. Okay, even 1 week, 1 weekend class is fine. Sorry, I have already committed on days. Here also, weekend is also fine. Okay, I think, yeah, I mean, the problem is I'm giving 3 days off for a week so that even if there are any backlogs in revision, so you will cover that in Friday, Saturday, and Sunday. Okay, so I hope that should be manageable. Okay, weekend not possible for me. 2 hours per day is good. Okay, yeah, on an average, almost everyone is good with 2 hours. Okay, yeah. Okay, guys, thanks for that. Okay, so I want to give a 5 minutes break. If you have any questions on these things, till now, whatever we discussed. So on replication factor, on blocks concept. So, and again, the fault tolerance or the failure scenarios, I didn't cover all the failure scenarios. So Akhil asked one scenario that I explained, but there are a couple more scenarios that I will slowly cover. Okay.
Shiva, I have one question, Shiva. This is Lakshman.
Yeah, Lakshman.
Shiva, is it normal to have high availability on name node, or is it not usual?
As per Hadoop 2.0 architecture, it is normal to have. And okay. I didn't come to that place yet. I will be covering that as well. Okay.
Okay, thanks.
We will cover that. So what is high availability mode and what is the responsibilities of data node, name node? So those things
sure.
I didn't get.
Thank you.
Okay.
Got it.
Okay. So next, so I talked about the blocks. So HDFS is a block structure file system. So 128 MB. So multiple data nodes need to be referenced. So to read any file, so multiple data nodes needs to be referenced. And the list of data nodes which need to be accessed is determined by the file system metadata stored on it. So we have seen the writing anatomy and the steps involved in writing. So next, let's see the reading of it. Then almost you will understand the responsibilities of your name node and data node also. Also, I have one similar diagram. Okay, I think this diagram looks better, cleaner. Okay, the same like this. This is about HDFS file system. So one client, one name node, and multiple data nodes. So reading data in HDFS cluster. So I received a request from user. So writing file in HDFS, check. What about reading then? So let's ask the client machine or the edge node again. So Mr. Client, please read this file for me. Okay. So please give me info on this file. So user sends which file to read, and edge node or client machine asks the name node, I want to read this so-and-so file. And your name node will have a metadata. What is the file name? And file name colon, it's all list of block IDs. So how many blocks that this file is having. Okay, let's take this file is having 3 blocks. So block 1, block 2, block 3. And this name node also maintains where is this block 1 is located in which data node, at DN X1. The first copy is in data node X1, and the second copy is in data node Y1, and third copy is there in data node Z1. And similarly, block 2 is present in data nodes X2, Y2, and Z2. And this present in this thing. So it replies all this information. So where all it should, it can find all the 3 blocks. So all the 3 blocks where it can find all the 3 copies. I reply a list of all blocks for this file. A, the list of all blocks for this file, and B, list of data nodes for each block. The list of blocks and list of data nodes for each block. And sorted by distance from client. So whichever is the closest one will be given in the first in the list, next closer in the next, and the least closer in the last. Now, that's it. Your name node, you don't need, client don't need name node no longer. Now, I know how many blocks to download and the data nodes where each block is stored. So I download each block. In turn, it downloads entire file, right? So download data from the nearest data node, the first in the list, X1, X2, and X3. So it goes to X1 to get the block 1. It makes a request, please give me block 1 or block 2 or block 3. Give me the block N. So it sends the data for block N. Okay. Now again, the same like you. Here is the question: what happens when the data node is dead, or does not have the data, or the data is corrupted? Okay. So actually, HDFS can very elegantly handle these faults and more as well, as we will see in the next. Okay. Doesn't RM have any role in the read process? Just reading, just downloading the contents, just getting the file back into your local file system, you don't need RM. You're processing, just reading record by record and processing some, extracting some search keywords, and minimum processing is there, then your RM will get involved. Just to reading the file back as is or downloading the file, the entire file, it doesn't involve resource manager here. Yeah, good catch. You know. So why? Because I used to say that while processing or while reading the files back, your resource manager will come into picture, right? But so when you are reading the entire file, downloading that back to your so client machine, that time you don't need to interact with resource manager, RM. Okay, so this is the flow, action flow while reading the file back. Okay. Now you understood. Now you can easily understand the remaining slides in this. The responsibilities of name node and data node. Okay, so there is a command to check all the files and all the blocks in your Hadoop cluster. So this command, fsck file system check Hadoop FSCK / means this is a root folder. Hyphen files means it gives you all the files in that HDFS file system. And if you ask for hyphen blocks, it gives you all the blocks in that file system. And all the block IDs for those files. And there is other way of checking your files also. That is HDFS web user interface. So HDFS web user interface, you can check. So let me run that command for you. So Hadoop FSCK / files. It gives me all the files in my file system. Okay. So since this is my VM and my laptop memory is 8 GB, so you may see some delay in getting the responses for these commands, but in real time you will not get that. Okay. So my cluster status is healthy, and total size in terms of bytes, and total blocks, how many blocks are there, minimally replicated, and what is the default replication factor that I have enabled in this pseudo cluster, which is 1. Average block replication is 1. Is there any missing replicas? Are there any corrupted blocks? And how many number of data nodes we have? I didn't talk about racks now. I didn't talk about racks yet. Okay. So these are the files that you have. This is one of the Varlag Hadoop Yarn apps file or directory. Under that, this is the file. So how many, this is the size of that file. How many blocks are there? Only 1 block. Okay. So this lists down only the files of your HDFS. If you want also the blocks, you can check. This is through command line. Let me show this through web browser as well. You can browse through your cluster status and all the HDFS file system through the HDFS web UI as well. Okay. I clicked on Firefox. Let me. So file system under path root is healthy. Okay. So let it get loaded. So you can access your HDFS web UI with name node host name, where in which machine your name node service is running. So in my case, in our local, in our pseudo cluster, in our Quickstart VM, my name node is also running on the same machine. So my name node's host name is quickstart.cloudera that we have seen yesterday. Either you can use that host name or IP address, and you should refer to the web port number 50070. So it gives you your name node status here. So it tells that. So your name node is running on so-and-so host name on 8020 port number. This is the TCP port number. This is the web port number. You should identify these two differences. Okay. And if you try to access your name node web UI with this 8020 in the browser, it gives you a message that seems like you are accessing some TCP port number. IPC, inter-process communication. So it looks like you are making an HTTP request to an Hadoop IPC port number. This 8020 IPC port number means inter-process communication. Within HDF, let's say, suppose you have a file in HDFS and you want to you want to copy that HDFS file from one Hadoop cluster to another Hadoop cluster. That means one cluster to another cluster, one process to another process, inter-process communication. There, you should refer to this 8020, especially when copying data from one environment to another environment, or referring a HDFS file in your MapReduce. Even there, it's optional. It looks for core-side.file properties. But sometimes during your programming, anywhere if you need to specify your name node host name, there you should give this default 8020 port number. Okay. And apart from that, apart from your programming, if you want to open your file system in your web browsers, you should refer to this HTTP port number, this or web port number 50070. Okay, I hope you are able to catch the difference between these two. Okay, actual daemon process on your machine is running on this 8020 port number. Okay, but in browser, if you want to access, this is the HTTP port number. Okay, and it gives you the summary of your HDFS health status, like so security is off or safe mode. I didn't talk about safe mode yet. We'll be talking slowly. And what is the configured capacity? How much distributed file system is used? How much is non-used? And percentage of utilization, all that stuff. Okay, so this is the summary of the file system. Also, you can list down all the files using the go to utilities. Go to file system, browse file system. I think even I should download the latest 5.7 version and see how it works, because this is damn slow. Okay, still loading. So this is the browsing directory. You can give the root path /. What I can do is I will kill some of the services. I will free up some RAM memory. Let me kill some processes which are not needed, at least for now. Bootstrap. Sudo kill. I want to run it as a super user command. Sudo kill -93896. I don't want that is related to Spark, I think. And 5085. And this master is also Spark only. 3973. Job history 7, this bootstrap 4904, and REST server also I don't need. 3229. And I will stop this one also. Okay, so under my root directory, I have these parent directories like HPA, Solar, Temp, User. So if I go into User, so under this user, I have these many users. I have Cloudera user, I have History user, I have Hive user, I have Woozy, I have Spark. Okay, so if I go into Hive, I have warehouse folder. You can see all these things, but I don't have any data in this. Okay, let me take into Cloudera. So block size is the 128 MB, but the replication is only 1, and the actual size of this file is just 8 bytes. Okay, I was let me take into some or data files. Let me take into data files. Yeah, so this is at least some 660 KB tweets.csv. You can see this blocks information here. So you can see the file permissions, owner and the group and the size of the file, replication factor 1, and the block size is 128 MB. So that means obviously the file size is less than the minimum block size. So then it will have max of 1 block. And so it shows that blocks information. I have only 1 block, that is block 0. If you have multiple blocks, then it might have displayed those list of block IDs here for this file. And so if you select block 0, that block information is this. And if you have multiple blocks, then it lists down them here. And if you select each of those blocks in the drop-down, that block information will be displayed here. The block ID, what is the block sequential ID, and the block pool ID. So it maintains those blocks into some pools or based on some stuff. Okay. And so what is the size of this block in terms of bytes? So which is like around some, okay. And where is this block located in which data node this block is present? So since I have only 1 data node, in your quick start VMs, you will always see this as one host name only here. Okay, but I will try to show the real-time cluster as well, show you blocks residing on different host names. Okay, maybe tomorrow I will try to show that. Okay, on cluster how it looks, it distributes the data, or let me give it a try. No worries, I will show it tomorrow. Okay, I will write it as action item. We'll write as an action item. Show web HDFS HDFS web UI for real cluster. Okay, so I will show you that, and all blocks of replication and multiple data nodes, all that information. Okay, so here in our case, under this, again, you can see the list of data nodes in this. Since we have only 1, you can see only that data node information here. And in the overview, that you have seen that summary. Okay, that is itself. and snapshot and startup progress. These are rarely we bother about. Yeah, this is the utilities section, browsing the file system and checking the log files of your name node and data node. You can do this. If suddenly, all of a sudden, if data node goes down, generally developers, big data developers will not check this. Hadoop admins will check these log files. If data node goes down, that particular data node's log files can be accessed from here, and they check what is the error message or warning message it has thrown before getting shut down. Getting down. Okay. So advantages of maintaining large block size. So one major advantage I was telling, to reduce the seek time, to minimize the number of seeks, and thus by reducing the overall seek time. Okay. So another benefit, no need to store all blocks of a file on the same disk or node. If you divide a huge file into multiple blocks, you don't need to store that entire file in one machine. You are distributing the storage load onto multiple machines. You are leveraging multiple machines at a time. And that helps while processing as well. Since you are distributing that blocks into multiple machines, while reading that data back, it can read all of them in parallel. Okay, while processing or just downloading them, it can do file by file, or just to process and find out some search results or something like that. It will parallelly start. That is where the parallel processing capacity comes into. Okay, so how fault tolerance is achieved? So since you are splitting that files into blocks, it splits them into, it copies them. Why that number before every daemon is given? Okay, port number 50070 is always same, and 8020 can change. 50070 is always same. If your admin wants to configure, they can configure. But ideally speaking, in real-time clusters also, they keep the same port numbers as is. Port number 50070 and 8020 are the default port numbers. Okay. And if for any specific reason, if they want to change, they can change both the port numbers. Okay. Again, this port number, they can specify in the core site.xml file. Okay. And there is one more question, why that number before every daemon is given? That is the process ID. These are the processes, right? These are the Java processes, and this is the process ID by which you recognize them. Okay. And that is for your question, Akila. And Neetu, why some pseudo process have number but blank? Where is that? Oh, okay. Might be the same pseudo process, or let me check the long messages. Might be these processes got killed and didn't clear these process IDs. Okay, that might be. Okay, I'm not 100% sure. Okay, but you don't need to worry about that. Okay, so that will not come into our context anywhere. Okay, so with the help of blocks, so you are reducing the seek time, and you are able to distribute blocks across the machines, and it is easy for you to maintain replications as well on blocks. Okay. Next, name node responsibilities. You have seen it is storing the metadata about your file system. So file system metadata is stored on name node. File system metadata means list of all the files on your HDFS and their file permissions. File permissions means, so this information, whatever you are seeing here, so whatever you are seeing in this information, so it will stores all the list of the files and their permissions, their owners, group information, the replication information, the size of the file, block size of those files, and the block IDs, including the block IDs for that file. So this information, so here anywhere, I mean, you are not seeing the actual contents of these files. You are just seeing the metadata about these data sets. Okay, so that metadata, it maintains in a file that is called as FS image in the name node. Okay. So I think that's it. I will stop it there. I will cover the complete roles and responsibilities of name node and data node and secondary name node. So all these responsibilities I will cover tomorrow. Okay. So just I took the concept of blocks today and explained the advantages of blocks and how does the files get written. Okay. And how does files will get read back using that blocks. Okay, and I have shown you the HDFS web UI, web user interface. That's it. That's the gist of recap of today's session. Any questions?
Shiva?
Yeah.
See, master node and data nodes are there. Every data node having the 3 blocks. Same, like it is replicating, right? Every data node will process the 3 blocks or only 1 block?
Only 1 block while reading it.
While reading it, okay. See, suppose data D1, D2, D3 is having the 3 blocks, B1, B2, B3 like that.
Yep.
Suppose it is already processed everything. Okay. Whenever it is supposed to give the data back, process it back, at that time if it is corrupted, what happened?
At that time it is corrupted. Okay. So as I was telling you, right? So D1 is having B1 block, right? Okay. And D1 is corrupted now. D1 is dead now. Okay. So now what will client do? It again makes another 3 attempts. So up to 4 attempts. So even after 4 attempts, if it fails, then it marks that task has failed, and it reports that to name node, and name node puts that data node into blacklist. And B1 is just 1 copy, the first copy in D1. The other 2 copies will be present in some other data nodes. Maybe let's assume D4 and D5. Then in that pipeline, when client asked for name node to give all the blocks information. So when you see this, where is this? This is a write, right? Let me show the read one. Okay, so it received for block 1, X1, Y1, and Z1. So now X1 is failed. After 4 attempts, it marked this as a block. Then in this pipeline, it goes for Y1 and requests that B1, block B. Okay.
Okay. I got it.
Any other questions? Yeah, no problem. Welcome. Anand, Neetu, Soumya, any questions? Rakesh, I think you pinged a question there. So what if while writing the storage space is reached to max in a data node, then how it writes the remaining blocks of the same file? This is exactly a good, perfectly good question. You will get out of space reached error message. Okay, it's a hard stop. If you don't have enough space in data nodes, you will not be able to write that. You will get the storage space limit reached. Okay, but if only one data node is reaching that max limit and other data nodes not reaching, means your name node will have that information. How much percentage utilized your each data node is. And while picking the data node for writing itself, it picks a data node which is having enough memory, enough storage space. Okay, if there is no option, if all the data nodes are 99% utilized, then it picks something which is better to go with. And even if that fails, you will get the hard stop error messages. If you have only one data node which is 99% utilized and remaining all others are just 50% utilized, first of all, your name node will not allow that scenario. Okay, so when your admins will not allow that scenario, they will constantly keep monitoring so that no data node will be overutilized and no data node will be underutilized. If they feel like that data nodes are properly balanced, they will run a command called HDFS space balancer. HDFS balancer, then some of the blocks from the 99% utilized data node will get copied onto 40% utilized data node and making both the data nodes coming around 60% or 65%. Okay. Yep. Any more questions?
Shiva, what happens when the data nodes fail? The block fails. Like in this example, X1 fails. Then what do we do?
It reads from Y1. That's it. So block one is replicated on X1, Y1, and Z1. X1 is failed. You will read it from Y1.
No, I was talking about writing. Writing itself, it fails on X1.
Writing itself is failed on X1. Then it will write on to Y1.
Oh, it will still go and write on Y1.
Ideally, your client will write only onto X1, and X1 will copy that into Y1, and Y1 will copy that into Z1. But writing into X1 by client is failed. Then client will write into Y1. That's it.
Okay. And if all three fails?
All three fails, it attempts four times on each data node. Then it sends that, boss, you gave me the corrected data nodes, put them in blacklist. It puts X1, Y1, Z1 in the blacklist, and it selects the next one. Not even the next one. It throws the hard stop error message. All the failed. Writing is failed. That's it.
It does not log that record somewhere, right? It does not.
It notifies that to name node. It throws an exception. Write failed exception.
So will we lose that data?
You will get this exception message into the logs. So based on that rare scenarios, you should rerun that, re-upload the data. You will have anyway in client, right? So you'll need to retry after fixing your data nodes issues.
So Shiva, in this case, if it fails to write to these three data nodes, it'll totally throw a hard stop error.
Yes, hard stop exception message saying that writing into that file got failed. Some IO exception is right.
Okay, but I'm assuming there might be more data nodes, right? It won't keep trying. more than 3 times?
So after 4 attempts to each.
Yeah, I know 4 attempts.
Yep.
But I think like 4 attempts for each data node.
Given
For
data
X1,
node. Yep.
4 attempts, for Y1 4 attempts, and for Z1 4 attempts.
Yep.
And after that, won't it try to go to some other data node?
No, it will not go automatically. Yep. It will fail there, and your name node will get notified. And again, you need to re-upload that file, because there should be some limit, right? Otherwise, it will be a never-ending. It may enter into deadlocks.
Okay.
Okay. Because
how is the process like? Once it stops, it throws an error.
Yes.
Then you just rerun the job and it does it again, or?
Yep. You need to rerun the job after fixing your data nodes issues. I mean, at least majority of your data node. And the next time it will get different set of data nodes. Obviously, if even those data nodes are having issues, then we should fix the data nodes issues. Then write your data. Is there a limit that each data node can contain that these many blocks? This is decided by how much hard disk capacity that each data node is having. Let's say each data node is having 20 terabytes. So 20 terabytes by 128 MB. Leaving, let's say out of 20 terabytes, if you keep 4 or 5 terabytes for buffer utilization or temporary files, 16 terabytes by 128 MB. That gives you the maximum blocks that you can store there.
Shiva, I have 2 questions.
Yeah.
Is there a rollback?
Rollback of your file status.
Of the saving the files, of the saving the blocks?
Rollback. No. So once file is written to HDFS, that's it written.
Okay. So like, if I have suppose 500 blocks, and out of that 251 it failed. At 251 it failed. Will it continue loading the remaining ones, or I stop and load the first?
No, it will have the 250 blocks loaded, and 251 failed. It throws the error message. It will not continue further.
Oh, so that's a hard stop.
That's a hard stop.
Okay, you have to refix that and reload it.
Yeah. The problem is if you make it continue, anyway that's lost. One block is lost. You can't copy that one particular block. It's lost. Right? You have to re-upload the file again.
And you have to start doing at 251 again, right?
You, ideally speaking, yes, but generally what we follow real time is we clean up that data and we rerun the job, or yep.
Okay.
There might be some CRC checking errors that you receive sometimes. It will work. Ideally speaking, it should work. So re-uploading, just copy the missing blocks. But the problem is when you are copying from one environment to another environment, and sometimes in processing the job, you will get some CRC check errors. One might got uploaded during one timestamp, and the others might got uploaded other timestamp. And the CRC length, cyclic redundancy check in the network, you know that, right? Network terminologies. So in practical, we clean that directory and we re-upload the file. That's how we deal with it. So what happens when two clients try to write into the same HDFS file? Same HDFS file, it throws a duplicate. Our file already exists for the second client.
Okay. And Shiva, you're going to take some scenarios, right? In the class, how to fix it, how it fails, when it fails, all that stuff, right?
That failure scenarios I will be covering. Don't worry, I will slowly cover. We'll come there. Okay. So different. Yep.
today when you time, I would like to go through those. I've installed it, but I'm lost with the whole thing. Where to find what?
What happened? I mean, what did you lose?
So, I cannot launch the command prompt, right? How do I launch the command prompt?
Oh, in the Quick Start VM.
Yeah, in the Quick Start VM, right?
The terminal is there here, right? Here you can see this. This is the command prompt. Terminal. Here you will find. Okay. Yeah. And I have a question. Different block data of replicated data is given. What happened? Different block data. Is this answer to the above question, Akila, or you are asking question? What happens when two clients try to write into same HDFS? Different block data of replicated data. Okay. Okay. Different block data of replicated data is given. I didn't understand this. Maybe you can unmute and you can explain.
If two clients are accessing the data,
Okay, you're telling in the time of accessing, but he is asking at the time of writing.
Okay.
Try to write into the same file. Then obviously you'll get like file already exists exception. That is a hard stop.
Okay. But we have an option command like if the file exists also we can override and write it, right?
Exceeds means exists and okay. So that is overriding, and that means deleting and rewriting. That means again the first client is lost.
Yeah, and then what will be the scenario at that time?
Obviously, whoever writes second, those changes will be persistent, and the first whoever writes, those will be lost. That's something like deleting the existing file and rewriting, force writing.
Okay, but the first glance information is lost totally, or
Yes, it's lost. File. If you overwrite the file, it's lost, completely lost the first.
Okay, thank you.
Yeah.
Okay, thank you, Shiva. Thanks a lot.
Yeah, thank you very much. Bye-bye. Thank you, guys. Bye-bye.